Welcome back to the channel where we discuss about material science and metallurgy on daily basis. So let us continue our discussion. And in the previous class, we have seen about the one of the phase diagram, which is isomorphous system. So let us proceed. So in this, we have already discussed that how the phase diagrams are classified into different types based on their solubility and all. So this was the first example that we have taken, wherein isomorphous system, two components are completely soluble in the liquid state as well as in the solid state. So liquid phase and solid state. So here, this is the liquidious line above which everything will be in the liquid state, and this is the solidus state. So this is liquidious state above which liquid phase, and this is the solidus state below which everything will be in the solid state. You must be wondering what will be in between these two lines. Like you rightly guessed, yes, you have a two-phase region wherein both liquid and solid present in this two-phase region. And since this is a isomorphous system, let us discuss next type, wherein two components are completely soluble in the liquid state and insoluble in the solid state. So for this construction, if you recall, we may see that this is extreme end wherein maybe A is 100%, B is 0. And as usual, on the other extreme, you have A 0 and B is 100. So obviously, these two are the pure metals. When it comes to in between, and in between these two, obviously they are alloys, and obviously there is a solid solution. So you must understand, as and when there is an alloying element added, that means B is added into A, there will be decrease in the temperature at which this transform the liquid to solid. That is, the freezing temperature decreases or drops. So this is quite often observed in many cases also. So this is the consideration if you take from left to right. Like as we move from left to right, you have on the x-axis B is alloyed in A. So when B is alloyed in A, why I am saying B is alloyed in A? Because our major constraint here, if you see, it is the A part, that is A is 100 and small amounts of B is alloyed. So when B is alloyed in A, you have a small amount of temperature at which the freezing will vary, that is liquid to solid. So here, this is the beginning and this is the ending of transformation. And furthermore, if you go, you have, this is the beginning and this is the ending of transformation. So if you have noticed, the beginning of transformation is decreasing, but since it is completely insoluble in the solid solution, there is a constant temperature at which the complete transformation is taking place, and there is no solubility between the two solid solutions. So that is the line in which is again an horizontal one. So there is a beginning of transformation, but ending of transformation is a constant temperature, and this is the constant temperature at which end of transformation is occurring. And this is also happens to be same across all the alloy phases. Now, as we were discussing that, when we are moving from left to right, B is alloyed in A. Suppose you take an instance where you go from right to left. So when we take from right to left, so let's say this extreme is considered as A is 0 and B is 100. So when B is 100, pure B. When pure B is there, then you take anything from that extreme. So it is like A is alloyed in B. So when A is alloyed in B, obviously the freezing temperature drops from here. So as you can see, from both the extremes, there is a decrease in temperature of their freezing point as the composition is increased. So that can also have a common point, which happens to be the end of solidification line as well. So listen to this statement again. So when there is a external entity added, the freezing temperature will no longer be at the same pure metal, it drops. So from both the entities, it has dropped and it has reached to a common point, which happens to be a constant end of temperature, end of solidification line as well. So that is a point which is called eutectic point. And this is very similar to what we have seen even in the pure metal, a direct conversion of liquid to solid. And the name itself says when two metals are completely soluble in liquid state and insoluble in the solid state. So this below bottom, this solidus line is insolubility, which can be both the entities of A and B present as not soluble in each other. So both A and B are present. So so I hope you have understood about the construction part. So let us remove the construction element and then see only the diagram. So a diagram looks in this fashion, wherein you can see this is the liquidious line, above which there will be a liquid, and this is the solidus line below which insoluble A and B are present. So both alpha and beta, let's say A extends to alpha, B extends to beta. So both alpha and beta are present in this two-phase region here. So unlike in the case of isomorphous system in previous phase diagram, where it is completely soluble and we have represented with only one element alpha, here in this case, since they are insoluble in each other, you have both alpha and beta. So when we write it in terms of equation, it is like liquid converts into two solids, solid A plus solid B, and this mixture is called eutectic mixture. But very important point to be noted is it happens only at this temperature and composition. So only at this temperature and composition you end up getting a eutectic mixture of alpha and beta, or solid A and solid B. Anything less than that, you have an element of solid A plus the eutectic mixture, solid A plus solid B. So that is very important point to be remembered, because here you have a two-phase region wherein there is a liquid and also solid A. Similar is the case on this side of the eutectic region, wherein you have liquid plus solid B. So when anything is in this composition that is more than the eutectic composition, you'll have a eutectic mixture plus solid B present. So this is eutectic reaction, and this is the eutectic phase diagram. Nothing to worry if you have not understood to the fullest extent, because this eutectic mixture we are going to use in a very important phase diagram called iron-iron carbide phase diagram. So moving on, we'll have another thing which is a partial eutectic. So in the previous case, we have seen that it is completely soluble in liquid state and insoluble in the solid state. But there can be a possibility wherein the solubility may not be completely in the solid state. There may be a composition up to which it is completely soluble, and beyond that insoluble. So similar is the case on the other side. So as you can see here, we have a region, or we have a composition up to which it is completely soluble in between each other, like in case of isomorphous, and you'll have a single phase here, alpha, and it can be on either sides or it can be only on one side. So you can see here as well, you have a composition up to which it is completely soluble, and you have beta. That means both A and B are able to dissolve like in isomorphous, and you are able to get only complete soluble single phase. And beyond this line, you can see this line, beyond this you have insolubility like in the eutectic. So you have both alpha and beta not soluble in each other. So this is a unique feature, and of course this is same as the previous one. So you have a two-phase region here as well as here, wherein liquid plus alpha, liquid plus beta. Now, if you ask me, this is liquidious line, okay, and this is the solidus line. But what is this line? This line, which is come new, this is called solvus line. Solvus. So this line will separate complete solubility to insolubility, and these lines both here and here are called as solvus lines. So this is about partial eutectic reaction. So the equation remains same. Liquid will transform into two new solids, alpha and beta, and that mixture is called eutectic mixture. But this is a case of partial eutectic system. Moving on, there can be a possibility wherein the two components are completely soluble in both liquid as well as solid. But if you have noticed, their melting points generally lies between the melting point of A and B. But there can be another possibility wherein the A-B composition may have a different melting point than A and B. That means it may be increasing and decreasing or decreasing and then increasing. That comes as a congruent melting intermediate phase. So the best example is magnesium and tin, wherein it increases and then decreases. So this is called as a congruent melting intermediate phase alloy. Next is a peritectic reaction, wherein the liquid and solid will react to form a new solid. So this happens particularly when you have a wide range of melting points between both the entities. That means if you see in this case, you have a very wide range to cover. And in this case, the liquid will react with the newly formed solid to give rise to a new solid. So you can see this is the phase. So you have a liquidious line and above which there is a liquid, and this is the partial eutectic kind of thing, wherein you have a partial alpha, and beyond that it is not soluble. And this is the region where you have both liquid and solid present. Since the temperature is wide enough and it has to travel a lot of range to complete, so liquid will react with this solid form and gives rise to a new solid beta. And this is happening at this point P, and the reaction is called peritectic reaction. And this is observed in silver and platinum alloy. Next is about the components completely soluble in liquid states, partially soluble in the liquid state, which is nothing but monotectic reaction. So you have liquid not completely soluble, and you have giving liquid gives rise to a new liquid and a solid called partial eutectic, monotectic reaction. Then we have complete insolubility in liquid and solid state. So you can see in this region, both the liquid A and the liquid B are not soluble, and you also have solid A and solid B are completely insoluble. The example is copper lead. So these are the things which are happening so far, what we discussed in the liquid phase. That means on the left hand side, we have liquid and liquid transforming into different types of transformations, but there can be a possibility even in the solid state. That means even after solidifying, there can be some transformations taking place, and this is because even after freezing, the temperature is still hot, and by the time it reaches to room temperature, there can be certain transformations taking place. So we are going to discuss about these transformations in the next class. I hope you have a good time. So do subscribe and then encourage to give more updates on such topics next time. So see you next time. Thank you.